Today we start chapter 6, which will be a light introduction into differential equations. So we start today with the slope fields and Euler's method. Let's first discuss what is a differential equation. So as the name says, it's an equation involving independent variable x, let's say, then unknown function y of x, and certain derivatives of that y. So y prime of x, y second prime of x, up to y and derivative of x. So if we have some algebraic equation connecting them like f of x, y, there's not enough of x, y2 prime, yn equals to 0, this would be differential equation of order n. In this course, we'll just discuss differential equations of the first order. So we'll do order 1. So that means that the highest derivative will be the first one, so they will look like this. Actually, very often we'll try to make it look like y prime equals f of xy, where y is obviously a function of x. So when this happens, we want to see when do we call a function a solution of this differential equation, obviously. So y equals, let me call it g of x, is a solution of the dE f of x, y, and y prime equals to 0. If what were we plug it in, it's correct. X, g of x, g prime of x really equals 0. Okay, so that's what we call a solution. And then sometimes, basically you already experienced some differential equations earlier. So for example, what if we have differential equation y prime equals x squared? This is differential equation because it involves a known function y. So y prime is there, x squared, and y is missing. But generally what is this? This is just what you did in calculus 1 or 2. Just you get y of x integrating. So y is integral of x squared dx, which is x cubed over 3 plus c. And we can say that this is, if we think of this as a differential equation, here is the solution. But then that solution involves c, and you remember the meaning, plugging different values for c, we get different solutions containing different points. So generally it's solution of that type. So if we have g of x, c, a solution, g of x, c is such that for a particular value of c, we obtain the solution. Of f x y y prime equals to 0. Then we call that a general solution. We call it a general solution. So one can think of it as a pool of solutions for different values of c. You keep generating different solutions. Let's see how it all works. Just have to kind of understand what we are talking about here. So, example number 1. It says the following: verify that y equals c e to the 4x is solution of the differential equation y prime equals 4y. Is actually a general solution. It's a general solution of that equation. I think. So how do we do that? We should basically plug it in and calculate the derivative solution. So if y is c to the 4x, then y prime is c times e to the 4x chain rule for x prime, which is what? C to the 4x times 4. But this is just y, so this is 4 times y. So really it satisfies the equation, so we checked it. Then the same problem could be asked for implicitly defined function, the same story. Number 4. Equation, so differential equation is not solved for y prime, it is more implicit like this. So differential equation, y squared minus 2 ln y equals x squared. Verify. No, sorry.
Hey.
Verify that the curve defined implicitly by y squared minus 2 ln y equals x squared is a solution of differential equation dy over dx equals xy over y squared minus 1. So it is solved for y prime again, but the expression is a little more complicated and involves both x and y. So what do we do here? We use implicit differentiation to get dy over dx, and that's all. Show algebraically that we are getting what they want us to do. So here it is. If we are dealing with someone satisfying this equation, then we differentiate with respect to x. With respect to x. That's what we did a minute ago, but this time we have to do it implicitly. So basically what? For implicit differentiation, I would prefer that we do long notation, so not prime, but we emphasize what we are differentiating with. So y squared minus 2 ln y is d over dx x squared. Here there are no issues, this is 2x. And here it's chain rule, it's 2y dy over dx, because that's what chain rule says, minus 2 times 1 over y dy over dx. So whoever satisfies this implicit equation will satisfy this equation as well. So what can we do here? We will multiply both sides times y over 2. Why is that? Just to get rid of that y in the denominator, and then we see everybody has 2, so that will generally make it look nicer. So we'll get what? Y squared dy over dx minus 2 and 2 cancel, y and y, so just dy over dx equals 2 and 2 cancels xy. So here it is. If you satisfy this equation implicit, you satisfy this, you satisfy this, you satisfy this. And then what happens from here? We can factor out dy over dx and get y squared minus 1 equals xy. And then what? From there, I probably close to the corner. But let me try to squeeze it in here. So if we divide by y squared minus 1, we get dy over dx equals xy over y squared minus 1, which is exactly the differential equation we're supposed to satisfy. So it was fairly simple. So again, the main things are what? This was our implicit connection. We differentiated, and then we got differential equation that we're supposed to get. All right, let's continue with a little more notation. So you see, when we talk about general solution, like this one, or this one, then C is undisclosed, so it's just whatever C you want to use that will give you a solution. When we specify a C and get really a particular function, that's called particular solution. And usually, how do we decide which value to plug in? We usually solve particular solution. Solution is a solution that satisfies additional condition, usually that satisfies particular conditions on Y, sometimes Y prime, not rarely. And that's called initial conditions. Basically, it's the same story like in calculus 1, among many, for example, anti-derivatives. You want to choose, so these are for different C's, then you want to choose particularly one that contains given points. So if I give you this point, then obviously this is the one to choose. To make it more specific, let's do an example again. So that example would be example number 12. It says the following: verify, again just verify that y equals 6 e to the minus 2x squared is the particular solution of the equation and here is the equation y prime equals minus 4xy, but there is so-called IDP, y of 0 equals 6. So among many solutions that exist there, they want exactly the one that contains this point. And it's initial because usually we think of x as time very often, so that's like at the starting time. So what do we do here? We just plug it in and check. So how much is y prime? Is what? 6 times e to the minus 2x squared times minus 2x squared probably, which is 2x squared. This derivative is negative 4x. And then what? This is your y. So this is minus 4xy, and really satisfies the equation. And then just plug in 0 to see if we get 6. Y of 0, 6 e to the 0, satisfied. So we checked. So nothing really here. Of course, the real problem is, and we'll also have a little taste of that, is when they give you this to ask us to find a solution and not to give us to verify things. All right. So here is now the story. So we start addressing that question: how do we solve a differential equation? So we will see here, and also in our differential equation course, that sometimes we are able to solve differential equations using different algebraic tricks and integration at the end. But that doesn't work too often. So for all the practical purposes, we really use either qualitative methods where we kind of get an idea how solutions behave, or numerical methods. So in the second half of this lecture, we want to address these two. So first thing is just what's in the title here are the slope fields. So if I'm telling you the story, I'll just give you the example, and along the route I'll just say what they are. So example, below the slope field of the differential equation, and the equation is y prime equals y minus x. So what's happening here? Generally, what differential equation tells you is that if we know where someone is, we know the trend of motion. It's basically like surfers, you know. Just if someone gives you the surf report, they don't know where you are because different surfers are in different places, but they say if you are there, the current will push you in that direction. So generally what we want to do is the following. We don't know where x and y are, but we can say the following. Let's just record for a few positions, and here comes the problem that actually if you just draw a few positions, it won't tell you much. We generally need software, and I'll show you that how that works. But let's see if we want to do it by hand. What I did in my notes, I chose a few points. So here are the point A, 0, 0. B is 1, 0. C is 1, 1. D is 1, 2. Then I started to go back. E is 1, 1.5. And F is 2, 0. So I chose these few points. So here is A, is here. And then let's say B is here. And then C is here. And D is here. And then E is here. And then F is here. So what happens then? Then we just, at each of those points, since we have both x and y coordinate, we just calculate y prime, and that's our slope. So for example here, m equals 0 minus 0, I just call slope 0. So m0 here, m equals 0, y minus x, it's 0 minus 1. So it's negative 1, here m equals 1 minus 1, which is 0. Let me draw this field. So how do you draw the slope field? Then at every point, you draw a little segment with the same slope as your curve. So here, 0, 0, it's 0, that means horizontal tangent line. So I draw, and that's my slope segment. So here it is. And then at B, it says negative 1. Negative 1 is like 45 degrees. So generally, it will be something like this. And then at E, I don't know yet, I didn't calculate it. At C, I get 0, so I get a flat. And then let me calculate the other few. At the D, m is 2 minus 1, which is 1. At E, m is 1/2 minus 1, which is negative 1/2. Here, m is 0 minus 2, which is negative 2. So at E, so let's see, at the D, function is increasing actually. So it looks like this. Don't make it too long. And then what else? At E, what happens? It's negative 1/2, so it's decreasing, but a little more flat. So here's flattening out and then increasing. And then at F, it is negative 2, so it's steeper. So that's part of the slope field, but generally for slope field to tell you anything, you basically need maybe 100 points, and that takes a little longer time. And obviously, it's a good idea here to use software, and there are many slope field applets. And let's see how it looks. So now I will draw this on the slope field. All right, so I just here pulled out one of the applets. So it's Matlet's published, Euler's method applet published by MIT. So generally, here, what you see here is the slope field. So those are few little segments that we drew. So generally, I just entered that function is y minus x, and then they just drew how many, like maybe 400 of those little segments. And generally, now we have some idea what happens in that field, actually. How will what will be the motion here. So if you look at this, you can see that there are some, if you look, close your eyes and then just look roughly, maybe you see some curves behind, and generally that's really, those are really the solutions of these differential equations. But generally it tells us about the trends, so we can say the following: if you are to the right, so you see y equals x looks like a straight line, y equals x plus maybe half or something, and then after that line everything goes like asymptotes, it goes down. On the left from that line it goes up, so that's like a dividing line in the behavior. So we get an idea what's happening, nothing precise, but we can get an idea of what's happening. And generally, what I'd like to do here is to address the next topic here, and that is Euler's method. So what happens in that Euler's method? We'll do the calculations on the board, but I'd like here just to show you what that Euler's method does, since we already have the screen up. So generally what Euler's method does is the following. So for example, here's my initial value problem. So I started my story here when x is 0 and y is 0.5. And then my equation is y minus x, and I would like to approximate that solution. So here's what I do. I actually approximate the solutions with the tangent lines, and that Euler method, you actually need to decide what is your step of calculation. So I'll talk about it in a minute, but let's see how that step works. So generally it approximates curve with a tangent line, and here's what it does. So when I go next step, what happens is just calculates actually like one of those lines from the slope field, and then the step tells us how long to go. And then when we come to this point in Euler's method, then we reassess. We use now a new position to see where, so it looks like here our slopes is a little bit flatter. So generally when we do next step, we have a new next zigzag line. And then we calculate the next one, the next one, the next one, and we calculate, and look, why are they longer and longer? Because curve is steeper, and then we approximate solution like this. If you go Euler's method with more calculation, like every 0.25, look what will happen now. These green lines are shorter, but they are kind of more accurate. It looks like more like a curve. And then, so more I do calculations, I'll get better and better calculation. Clear all this. So, clear. Start. Here it is. So we start here. Now we really go much more precisely. I erased the old one. So here is the one with lots of steps. As I said, the previous one was a little bit more off. And let me show you the actual solution. In this case, we really can solve the actual solutions here. So look, the actual solution is really that blue curve. Look, that yellow with a rough and big steps actually was a little bit off, but this one with a step of 0.125 was pretty good. And this is actually the idea of that Euler's method, which is the method for approximation of the solutions of differential equations. All right, let's explain what's happening with Euler's method that we just saw a minute ago. So generally, here is that solution that you are trying to estimate. You don't know what it is, of course. But here's the idea. So it's a solution of this differential equation, y prime equals f of xy. So here I just try to explain tangent line approximation. So here's point x0, x1, here are points A and B on the graph. So I know where A is. And I cannot find B, but I will approximate it by that point T. How do I get point T? I construct tangent line at A, and then I plug in x1, and that will give me T instead of B. And that will be fairly close, not ideal, but fairly close. So how does that work? So point A has coordinates x0 and y. Because it's on y of x. So I construct the tangent line. Tangent line point slope formula is y minus y0 equals m times x minus x0. What is m? M is the, we know from calculus, slope of the tangent line is value of the derivative at that point. So y minus y0 equals y prime of x0 times x minus x0. But then we use the fact that this is solution of the differential equation, so y prime is actually f of x0, y0. So we get y, and that's the whole thing. F of x0, y0 times x minus x0. So from here, I'll solve the equation y equals y0 plus f of x0, y0. And then, if I want exactly that point when x is equals x1, then I get y equals, and get the coordinate at t, y0 plus f of x0, y0 times x1 minus x0. And then the crucial formula for Euler's method, and I call that y1. So this is x1, and I'll call this. Not only that, this basically tells you if you start from y0 how to get y1. But now I will consider this my x0, y0, and then how to get new x1, y1. Actually, I will call them x2 and y2. So generally I use this as so-called a recursive formula. Recursive formula says yk plus 1. At every stage, take the previous one that you already obtained, which is yk, plus derivative at that point, xk, yk, times xk plus 1 minus xk. Usually, when we organize Euler's method, this is fixed. I usually call it h. So it's x2 and so on. So this is basically h. So it looks much nicer when you say yk plus 1, so new value of Euler's method. Take the old one, plug it into the differential equation, and multiply that by h. This is a recursive step of the Euler's formula, and let's see how it all works. So we will illustrate that on the example. Approximate. There is a one. All right, so approximate the solution of dy over dx. That's the one that we saw on the screen, y minus x. Y of 0 equals 0.5. And actually, more precisely, using n equals 10 steps. So in 10 steps, approximate y of 1. So we have y of 0, we want y of 1. So y of 0 is 0.5. Here is 1. We want to know, we want to approximate how much is that value at 1. So what do we do? We generally divide this, they said n equals 10. So our h from the formula, so whole segment is 0 to 1, so length 1. So h equals 1 over 10, which is 0.1. So what happens here? Probably didn't see that. It's outside of the screen. So h equals 1 over 10, which is 0.1. And then I can start the machinery, but just it might be a little problematic. How do you run the machinery? So let me erase this so that I have enough space and all this so that we can record our results. So the only thing that you need here is that formula that says yk plus 1 equals yk plus f of xk yk times h. So the way to do this, the best way is to generally put the value for xk. More space here. Put the values for yk, and then yk plus 1. So what we do is the following. We start with the beginning value. So at 0, what do I have? I have 0 here. I have 0.5. Plug in 0 and 0.5 here. Remember that f of xk, yk is actually yk minus xk. So in this case, I better write it that way. So f of xy is y minus x. So this will be yx yk minus xk. So here it is. So what do I do here? How do I calculate this guy? I'll do calculation on the side. So it would be whatever you have, 0.5 plus, subtract them on the line, 0.5 times 0.1. And this is 0.55. So who's this? This is your y0, and this is your y1. That's the next one. And then y1 is copied. Now that's your starting value. So now that's your yk on your next attempt. And how much is xk? Xk is just will increase by 0.1, 0.1, 0.2, 0.3, 0.4, 5, 0.6, 0.7, 0.8, 0.9. Why don't I do 1.0? Because on 0.9, this will be y9, this will be y10, and that's the value that I report. So what do I do here? It will be take 0.55, which is your yk plus, subtract 0.45 times 0.1. And that will be 0.55 plus 0.595. And then you keep going until you do 10 steps. The result that I get here, I will report. Actually, this process could be automatized. Obviously, this is a very easy programming, but even without using programming abilities of our calculator, we can automatize this process, and I will show you how we will get that process. Just let me record the result. So the result at the end, you will see that. The result should be 0.7031, and that is the value that we will report. So we will report here that the y of 1 is approximately 0.731. If you solve the problem, the real value is y of 1 is 0.64, so we were a little bit off. We did a little overestimate, but it's not that bad. And this is a fairly simple method. That's why we shouldn't expect spectacular results. So let's now see how a calculator can help us to automatize this process. All right, so how do we use calculator for this? Because this will take a long time. So here's the story. You don't even need a function mode. First thing is to enter your starting value, which is 0.5. And press enter. Why? Because calculator has a feature that this value here is input and this value here is answer, and that is actually what you can recover with the command yellow answer. So here's what I'll do. I will enter this formula that we just developed a minute ago, and I will answer it in the following form. So you remember it was yk plus 1 equals, and then it said yk, and that's my previous answer, so I'll say answer plus, then it was yk minus xk, so yk is my answer, minus value of x cannot be updated automatically, we have to do it, so value of x at this point is 0.0. And all that time 0.1. What is the advantage? Because later on I don't need to type this, I will just call this command and they will update the answer immediately. So what do they do? They read 0.5, plug it in, and we will get 0.55. Then what? There is a command second entry that recalls your last entry. So here is that, I don't need to type it again, but the good news is now it will update 0.55, we'll put for answer exactly as we need, which is y1, and give us immediately y2. And that was wrong. What did I do wrong? I forgot, because I see that, that this was done wrong. So I have to start it from, what did I do wrong? I didn't update here value for x. So from the beginning, so I'll do 0.5. And then I want that command, let me see if I can avoid typing it again. Here it is, that's the one. So I get 0.55. Now I do second entry for y2, but I have to update x value to be 0.1 manually, and this is better. I get 595, as you can see in the table. Then again, I go second entry, and I know I need to update this to 0.2. That's the next approximation. Then again, second entry. Don't forget this to be 0.3, and then second entry. Don't forget this for 0.4, and we keep going. So that's second entry, 0.5, second entry, 0.6, and I'll use that as a counter because when I enter 0.9, I will be done. Second entry, 0.7. Entry 0.8, second entry 0.9. Here is your result. And that result is what I reported, just rounded through to 4 decimal, 0.7031. So it was, much safer to do it this way. This is almost like programming. The only thing, we have to press enter all over again and to adjust the x value. And as you saw from that applet, this approximation with the step 0.1 should be fairly decent. You remember when I was on that applet, when step was 1/2, it was quite rough, but then the shorter the step, the closer we are. And of course, if you really want better approximations, then you either make more steps or learn a little more sophisticated methods. We don't study them here. There are methods that converge much faster and better than this one, but I think for a first contact with differential equations, this is quite nice for our basic purposes.